The Big Bang. Scientists believe that the universe began with a massive explosion, which has become known as the Big Bang. Why do they think this? Well, two main pieces of evidence: redshift and the cosmic microwave background radiation, or CMB. Redshift. Well, you're familiar with the change of tone when a car goes past you. This is due to a change of frequency of the sound. A higher frequency as the car approaches, a lower frequency as it recedes. The same thing happens to the frequency and therefore the wavelength of light from a moving source. If a light source is moving away from us, it will get a lower frequency and therefore a longer wavelength. If it was moving towards us, it would get a higher frequency, a shorter wavelength. As red is the longest wavelength of visible light, we say that the light source has been redshifted if it's moving away from us. If it was moving towards us, we would call it blue shifted. In the early 1900s, it was discovered that light from distant galaxies was always redshifted, suggesting that all the galaxies are moving away and that the universe is expanding. Edwin Hubble discovered that the more distant a galaxy, the greater the redshift. This suggested that previously they had all started at the same place. Now for the second piece of evidence, the cosmic microwave background radiation. The high-energy, high-frequency electromagnetic radiation that would have been emitted during and soon after the Big Bang would now have been so redshifted as to have gone to the microwave region of the electromagnetic spectrum. Theory suggested a temperature of this radiation of around 2.7 Kelvin. Scientists were looking for evidence of this, but it was actually discovered by accident by two radio engineers called Arno Penzias and Robert Wilson. This radiation appeared uniform in all directions. This was a bit of a problem as to if the early universe was completely uniform, why should it now be lumpy with regions of galaxies and regions of virtual vacuum? A study by the Cosmic Background Explorer satellite, known as COBE, in 1989 did show slight variations that help to explain this lumpiness of the current universe. Further evidence comes from the fact that the universe appears to be changing or evolving. Light travels at the finite speed of 300 million meters per second. It takes 8 minutes to get to us from the Sun, so we actually see the Sun as it was 8 minutes ago. Put another way round, if there were alien scientists on a planet over 65 million light years away, meaning the light takes 65 million years to get to them, they might look at Earth and see dinosaurs roaming round. If we look at the most distant galaxies, we're looking further back in time, and these galaxies have a different chemical composition to the nearer galaxies. This suggests that just as we no longer have dinosaurs on Earth, the distant galaxies probably now have a similar chemical composition to those nearer to us. The universe appears to have evolved or changed over its lifetime. Now a brief look at a theory which conflicted with the Big Bang theory. This was known as the steady state theory. It came about when redshift was discovered. It suggested that new matter was constantly being created in the universe and spreading out. This theory explained the redshift and was at the time followed by many scientists. It did not, however, explain the cosmic microwave background radiation or the evolving universe, and so was dropped in favour of the Big Bang theory. Now a run through some of the major events from the Big Bang to the current time. The closest we can get to the Big Bang is around about 10 to the minus 43 seconds. We're not sure of the temperature at this point because, as the universe would have been an infinitesimally small point, what's known as a singularity, the current laws of physics break down. But the four forces of nature would probably have been indistinguishable at this point. A little bit later on, up to 10 to the minus 34 of a second, there would have been a temperature of around about 10 to the 32 Kelvin. There would have been a constant interchange between radiation energy and matter. The radiation would become particle-antiparticle pairs, which would then meet up again to annihilate and produce radiation. The universe was expanding rapidly at this point, and so cooling rapidly. This interchange between mass and energy comes about because of what is known as mass-energy equivalence. This is basically that mass is just another form of energy. This is shown in the famous equation E equals mc squared, where E is the energy in joules, m the mass in kilograms, and c the speed of light in a vacuum. You'll learn more about this equation in the A2 part of the course. Going beyond 10 to the minus 34 seconds, we enter the grand unification era. Temperature has now dropped to about 10 to the 27 Kelvin. There's been a rapid expansion and cooling. Gravity is the first of the four forces to separate out, but at this point quarks and leptons would be indistinguishable. For some reason, which scientists are still not sure of, there was more matter than antimatter created. Moving on to 10 to the minus 10 seconds, what's known as the heavy particle era. The temperature now has dropped to 10 to the 15 Kelvin. The strong and weak force would now separate from each other, but it's still too hot for hadrons to form. The quarks and gluons would be floating around in a plasma. At 10 to the minus 7 up to 3 seconds is known as the light particle era. Temperature now just 10 to the 12 Kelvin. Hadrons can now form, and we get hydrogen and helium nuclei. Still not atoms, the electrons are still travelling free. 10,000 years after the Big Bang, we enter the radiation era, a temperature of 10,000 Kelvin. The energy is now mainly in the form of electromagnetic radiation. This would eventually become the cosmic microwave background radiation. At 300,000 years after the Big Bang, we enter the matter era. Temperature now 3,500 Kelvin. Atoms start to form as nuclei can now capture electrons. This allows photons to travel around freely. The universe now becomes transparent for the first time, and stars are starting to form. We're now up to 10 to the 8 years since the Big Bang, 100 million years. Galaxies now start to form. The average temperature of the universe has dropped to around 10 Kelvin, minus 263 degrees C. The galaxies including the Milky Way form, and the solar system including the Sun and Earth would have formed around about this time. That brings us to the present day, about 1.5 times 10 to the 10 years since the Big Bang. The average temperature of the universe now, that of the cosmic microwave background radiation, 2.7 Kelvin, and we have the universe as we see it today. So what about the future of the universe? Well, gravity acts over infinite distances, and so we'll be working to halt the expansion of the universe. Whether it will be successful or not depends on the density of the universe. Gravity acts between any objects with mass, and therefore the more mass within the universe, the greater the force of gravity will be. calculations suggest that we've only accounted for about 4% of the mass in the universe. The rest is known as dark matter. Scientists know very little about this at the moment. These calculations are based on the motion we see of galaxies. Other calculations show the rate of expansion of the universe to be increasing. This could be due to a thing called dark energy. Again, scientists know very little about this. Much research is currently underway. Here is a graph of the radius of the universe against time. Well, there are three possibilities. The universe could continue expanding, something like this. That would be if the universe had a low density. If the universe had what is called critical density, the expansion could slow down and eventually stop. This scenario is very unlikely. If the universe has a higher density, it could do this. Gravity could win, bringing the universe back down to a big crunch. At the moment, scientists are unsure as to which of these will be, although current evidence suggests that the universe will continue to expand.